This is John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State University, and welcome to Module 1, Part 1 of Industrial Energy Efficiency Process Cooling. So in this lecture, we're going to cover kind of a review. So people who are taking this course are generally engineering students, generally in the junior year or senior, which means we're assuming you've had thermodynamics and probably heat transfer as well, though that's not going to be as important. So we're going to cover a little bit of both of those things. We'll talk about units of measurement that we use heavily in this area, and we'll also present some definitions. So first law of thermodynamics, right? Energy can neither be created nor destroyed, or in this case we've shown here, energy in minus energy out equals energy stored in a given volume, right? This is defined thermodynamically around something called a control volume, where we can monitor all the things coming and going across the boundary of this control volume. So in the case of industrial processes, this energy in and energy out is usually carried in some kind of a flow, right? Airflow or water or some kind of a fluid. And if it's stored inside a control volume, if energy is stored, if the amount of energy stored changes, it's usually reflected as a change in temperature. So here's an example. I have a rigid tank where I've got water flowing in, water flowing out. We're assuming it's constant pressure and uniform flow rate. In other words, the flows are the same. And inlet temperature is 125 degrees, outlet temperature is 38 degrees, so there must be some heat being removed from this, and we'll call that Q cooling. And this is in essence an example of an industrial cooling process. So we know by applying the laws of thermodynamics that the rate at which heat or energy is carried in, which is m dot Cp times Tn minus m dot Cp T out, the rate at which energy is leaving this tank, minus the other way energy is leaving this tank through the cooling load, that must all sum up to zero, right? And so we have this expression that says that the cooling load in the system is m dot Cp times delta T. In more general terms, if we didn't have constant pressures, we would have a difference in enthalpies instead of the Cp delta T. But for a large number of industrial processes, we can assume constant pressure. So let's put some numbers to this. Let's say the water's flowing at 100 GPM. So we want to know what's the rate of cooling, and we want to know how we might refer to that in a typical operation. So and what we do this in, how we do this in industrial systems, we talk about cooling capacity in a unit of ton of refrigeration. So we're going to cover all those. So industrial flow rates, often volumetric, not mass flow rates, but thermodynamics, we want to talk about mass flow rates. So we need to, the bottom line here is, as is the case in all engineering applications, certainly the case in industrial applications, is watch your units very carefully. Make sure you're using the right units. So here's a page I took from the Engineer's Toolbox. Most of you know what this is. It's a great set of websites that describes a lot of useful information. Here are the properties for water. And specifically, I want to know the density of water, and it changes with temperature. So we come in at 38 degrees, leaving at 120. So I basically am looking at an average value of around 62.1. The specific heat doesn't really change all that much, but we have an average value of about 1.001 BTU per pound degree F. And those are the two constants we need to solve this problem. So we start with the flow rate, 100 gallons per minute. We convert to minute to hours. We know there's 0.1337 cubic feet in a gallon, 62.1 pounds per cubic feet. I just had that on the previous slide. So that means that 100 GPM comes out to about almost 50,000 pounds mass per hour. And putting that now into our original equation, we've got m dot in pounds mass per hour. We've got the Cp from the Engineering Toolbox, and the delta T, 120 minus 38, and that comes out to around 4.1 million BTUs per hour. And one of the things I want to point out from this is that in industrial settings, a BTU is a pretty small unit. So it's not that hard to get into millions of BTUs. So how do we get from there, from about 4 million BTUs per hour to tons of refrigeration? Well, this goes back to the early days of refrigeration, where we used ice to refrigerate, to keep things cold, and ice absorbed heat, and in the process melted. And so the question then comes, how much heat does it take to melt a ton of ice? And the answer is 12,000 BTUs. So that's the origin of a ton of refrigeration, is a ton of ice per hour, or 12,000 BTUs per hour, that can be removed by a system that's rated at 1 ton. Okay, so we divide that by 12,000 BTUs per hour, and so that process I described in that slide of 100 GPM of water going from 120 Fahrenheit to 38 Fahrenheit would require 341 tons of refrigeration to make that happen. Okay, so shifting gears. So that's a quick overview of how we would apply thermodynamics in a very basic way to industrial processes. And in doing so, I introduced the unit of a ton of refrigeration. In heat transfer, this is also a big part of what we do. And it helps us evaluate things like insulation on tanks and pipes. So you'll remember that there's 3 main forms of heat transfer: conduction, convection, and radiation. Radiation comes into play with fairly large temperature differences. We see it used more often in process heating, where we have steam pipes that are up in the hundreds and hundreds of degrees, as opposed to refrigeration, where the delta T's tend to be a little more modest. Conduction is by far the most common, and convection, of course, is conduction and mass transfer at the same time, right? It's conduction into a moving fluid. So conduction and convection are very common in industrial processes. Often we combine them together, and where we talk about an overall heat transfer coefficient, either an overall resistance, an overall conductance, and you'll see this equation in one of these 2 forms, where we have the area of the heat transfer either divided by an effective resistance or multiplied times an effective conductance U. So, and we'll come back to that. And just to wrap up this introductory lecture, let's talk about some of the terms we'll be using. So this is a course on process cooling, and so that refers to pretty much any way which we can remove heat from a product, a thing, or a flow, right? Now, refrigeration is a subset of that, and it specifically refers to a type of cooling process that uses a thermodynamic cycle, and it's almost always the vapor compression cycle. I say almost always because you might use absorption or adsorption, which is a way of using heat to refrigerate. A chiller is a specific kind of device, a hardware, that uses the vapor compression cycle. So it has a compressor, an evaporator, a condenser, but it's all self-contained, and it exchanges heat with another working fluid, usually water or water glycol mix. So a chiller has a refrigerant and a refrigeration system, but it's all self-contained, and what's coming and going and interfacing with either the building system or the industrial process is a secondary fluid, and that's usually water. The evaporator, that's the business end of the refrigeration system, right? That's what's getting cold. It's in the freezer, it's in the air conditioning duct, and it is just what it sounds like. It's the place where the refrigerant is evaporating and then absorbing a lot of heat. That's why it's cold. The other end of that, of course, is the condenser. It's where the hot vapor of the refrigerant condenses, and that's where the heat's being rejected, right? That's usually outside, on a rooftop in an industrial setting. Your home air conditioner has one of these things sitting on a small concrete pad outside the house, usually. We see a lot of water towers in industrial settings, and it's a device for rejecting heat. Very, very common, used in conjunction with chillers. So that glycol or water loop will be taking heat away from the chiller up to the rooftop, and it uses the evaporation of water to lower the temperature. So that's fairly common. And then the last device, and we're going to see these in the next lecture, is something called the evaporative condenser. It sounds like an oxymoron, right? You're both evaporating and condensing. And it's because we're condensing the refrigerant, but using the evaporation of water to drive that. And these are extremely common, particularly in the food processing industry. So one final slide, and then we'll wrap this up, is that this is a course designed for people near the end of their engineering career. So we're not going to spoon feed all the different details you need to it. There'll be problem sets. We're going to and we won't give you all the information you need to solve the problems. You're going to have to go find it. So have your heat transfer text handy, have your thermodynamics text handy, know your online resources. The engineering toolbox is a great one. And also, you should have this somewhere in your lab. If you're part of the Industrial Assessment Center, you have the ASHRAE handbook. That's a 5-volume set, and particularly the volume on refrigeration is one that'll come in really handy. So you'll notice over here, this is the table of contents from the refrigeration handbook, and there's quite a bit about the specific food industry, stuff about dairy, stuff about the fishery, the meat process, vegetables. I encourage you to get yourself familiar with resources like this. So thanks, and good luck.